So what we're looking at here, we're looking at this 3D stuff. Eh? So the two approaches we've got on this are one, to make it into a 2D problem by taking different viewpoints. We were looking down given axes. So the first one to look down was the y-axis on this little car problem. And when we did that, we noticed that A and C were both on the y, or B and C were both on the y-axis. A was not. So if we looked at it from the side there, we could make it into a 2D problem and solve for the reaction at A. So that was one way to do that. And then the next thing to do was to be looking down the x-axis. All right, and then what's going on there is now we knew what RA was. And so if we look down the x-axis, we eliminate RB, and we can solve for RC with a moment equation. So we're taking moments about axes is what we were doing. And then we can just go somewhere FZ to get the last one. All right, now notice, of course, the x and y axes intersect at the origin. That's where point B is. Okay, so what's going on here? We're just taking that 3D problem, turning it into a series of two-dimensional problems, then finishing up with some of Fy. Now, the other way to do it was to do a vector approach, and as I just mentioned there, I don't know what's going on here at the moment. The x and y axes, of course, intersect at the origin. That's where point A is. So if you took moments about point A with a big cross product, we're going to have three terms. Throw them all in there and run the numbers. What you'll do is generate those two moment equations that we did by taking the different points of view. So a cross product just does a moment for you automatically. So what you do there would be to do those three crosses and then collect terms, x, y, and z. Using the y equation, you could solve for RA. And then once you got RA, you could use the x equation and solve for RC. Okay, so.
Choose exactly what vectors we're crossing.
What's that? I'm sorry?
I'm choosing what vectors we're crossing.
What we're doing on the cross product is we're crossing position vectors that go from point A to the forces with the individual force vectors. So that's what we're doing there, if that answers your question. Yeah, so we're kind of we are using B as our point we're taking moments about, and then we just take in, like, for instance, that sketch is kind of small there, so this will be a little bit tight, but so like RB to RC, that's going 1.8 in the y direction. So that's 1.80 across with RC.
Okay.
And then we've got the force at the center of gravity, so we use the vector from the origin to the center of gravity crossed with that center of gravity force. And then we do the same thing with RA. And we have to do them all individually, so there are three separate crosses. We do all the crosses and then we add them up. Okay, so that's the deal with that. And when you do those crosses, what you do, again, you're just automatically generating those equations that we generate by looking at the different axes. Okay. And then you can finish it up with the sum of Fy equation to get the last one. So these are two methods to do the same thing. One, you do it visually, you turn it into a series of 2D problems. The other, you do it more mechanically using a cross product. Either method works fine.
Do you suggest one over the other as far as the test?
I think it's good if you can, as much as you can develop that by eye method, because the crosses just seem to take time, to kind of knock through them. And I think it's good, again, to develop that visualization. So I kind of like using the by eye method when I can, but don't push it too far, it can be a little tricky to do it, As we'll see on this next one coming up. All right. Other questions on that? We good? Okay, let's have a look at a trickier 3D problem. So let's look at a mast and some guy wires here. So I'm on page 472. So let's say we've got a simple boat here with a mast and a yard going across with a sail, and we've got those forces on here. And let's figure out what the forces would be in those and the ropes that are holding up the sail and the yard there. Okay, so we're going to look for the forces in EB and CD, and then the forces down at the reaction for the mast is what we're going to do. All right. So what we're looking at here is just a simple vessel with a single mast. Okay. There, that's what these things used to look like. You're looking at the height of nautical engineering about 1,000 years ago. So these things are real nice boats built in Scandinavia. Really incredible boats, really. I mean, look at the lines on that thing. And then you can see the design on the hull. They got a nice keel in there, so these things can go across the ocean, but then they broaden out quite a bit, and they can go up rivers too, which, there's just nothing in Europe that could keep up with these things, that's for sure. You got ribs in there, and then they use what they call lap strake construction. So they don't have real heavy planking as a framework. The hull itself is a lot of the framework. Now, the thing we'll look at here is how the mast was set, and that was set with something called a mast fish, is what they called this. And so there you're looking at one. So they have a large, heavy piece of wood where they'll set the mast, and they'll kind of lever it in, essentially. There's a nice picture of it right there. Okay, so they've got a wedge in there that they wedge in, and then they've got a keelson here, right on the keel, that's rounded out to fit the round mast, and then they can kind of wedge the mast into the mast fish, so to speak. Okay, so a real nice, simple system. Here's a picture of what they actually look like there. Okay. All right, now, so how are we going to model the bottom of that thing, do you think? How would you do it if it were, or how might you approach it? How would you model this mast fish connection? Yeah, there's two ways I think you could do it. You could model it as a pin joint, kind of a roller, more of a, you call it ball and socket in 3D. Yeah, okay. And what that would do, that would model more stress up on the cables, on the stays that are holding it vertical. Or you can model it as a fixed connection, and that would you'd have a moment here that you'd have to deal with on the mast itself. So there's different ways you can model this. And this is probably a good example of one of those things in the, when you're in industry where you're going to have to kind of scratch your head and figure out what to do. I mean, how the heck do you model that? I mean, you could start looking at different loads that this might introduce there to the bottom of the mast, but probably what I'd probably model it both ways, and use the pin joint approach or the ball and socket approach to design the cables, because that puts the maximum load on the cables, and then maybe design it like a fixed support too, and look at the moments that are building up in the mast itself. Probably what I do. I'd probably run it both ways. And again, just keep in mind that things out there in industry aren't quite as nice and clean as they are in the textbook. Okay, so so there you go. But you can see just how ingenious this is. How just people with hand tools are putting these things together. Pretty cool. So they could raise and lower the mast pretty quickly, and they could row these boats if needed. To lower it, they just have to get that lever out, and I don't quite know how they do that, but they just have to get that wedge out, and then the mast could just tip down. Okay. So they made this is one version of the ship. I mean, they're all on the same basic design. You know, again, you can see the lines of that. You know, and those things could go over open ocean, and then they could go up rivers as well. And then they had a trading version of it too. That's actually more of a warship. It's fast. There's nothing that could keep up with those. But then they had a trading version of it too, not quite, which was bigger, wider, more stable. And I believe those were called a Canar, but I'm not quite sure how to, don't speak any Scandinavian languages, so I don't know quite how to pronounce that, but the Canars they're wider and bigger, so they're more like trading type boats. Okay. Yeah, but they're both made on the same design. They're made with lap straight construction, that kind of planking that's hand carved and then fitted together. That might be a good picture of a Canar. This thing, it is kind of limited though. You can only go so big with these until they become too heavy. This design you could get so big, and they turned this into something called a cog eventually, and then that was in the Middle Ages, and then they kind of went more to the Mediterranean design with a frame and planks and caulking between the planks, as opposed to this kind of lapping plank design. That's pretty cool. But anyway, so let's have a look at how we might analyze this, okay? So what we got there, we want to find the forces in the sailboat mast and the cables. Let's find those cable forces too. Let's assume A is a ball and socket joint. So that's the assumption I'm making for this run at it. All dimensions are in meters, and the mast in the sail weighs 900 newtons, okay? Now, if I see something like this, you know, you can see you've got angles on these cables. I'm not going to be able to just kind of look at this in 2D. That's going to be a little bit rough to do that. So I would do a vector process on that to get those cable forces turned into vectors. Okay, so that's what I would do. So I would get the coordinates for A, B, C, D, E, and G. Okay. And then I would start working with coordinates to work through that to get those vectorized. The first thing I do is get those coordinates filled in. You have the dimensions on that sketch. So I think they're intermediate points of dimensions. Yeah, so that's going 1.4, 0.7, and up 1.1. So it's a little bit. Yeah, that one's. So it's an intermediate step. I got the coordinates up there if you. Is that okay on those coordinates? So B is 1.3, 2.3, 1.2, and C is negative 1.4, 2.7, and 1.1. D is negative 2.5, 0.5.1, and E is positive 2.5, 0.5.1. And G is 0.3.9. Doing all right with those? Yeah, question.
Where did the 5.1 come from?
The sum of 3.9 and 1.2.
Who's the dimension there? Oh.
Yeah, it's right there.
Doing all right? Okay, now what I want to do, I want to take those cable forces and turn them into vectors. Okay, so I just do the bit, the regular deal on that. We got a cable from E to B and another one from D to C. So that's something we've done, many times now. So take the two vectors and subtract them. Remember to switch the order on the letters. Take the square root of sum of the squares to get the length, divide that out to get a unit vector, factor it up by the force. Now the force is an unknown, but that's okay. So, we just go through and do that process there. Okay. Are you doing okay on getting DC? So like I said, on this one, I'm not gonna try and do it all just by looking at it. That's just gonna be a little difficult, okay? So I wanna get vector expressions for these things. These angled forces are difficult to handle just by kind of looking at them and figuring them out. You can do it, but it's difficult. So on the previous problem, all the forces were straight up and down. They're all Z forces. So that's fine. I'll do that 2D. But this one, I'm going to make vectors out of these things, okay? Because I want to get those components. Now, I might do some 2D work, but I want to get these vectors worked out so I know what the components are going in the directions that I'm interested in. Okay. So you notice on the next page on 473, I've got that mast and the yard drawn up. And notice how I've shown that those forces at E and D, I've got them broken up into 3 component forces with their magnitudes on them. So I can still kind of take a 2D approach when I draw them up that way. They're a little bit easier to kind of see which is pointing, which component of force is pointing which direction. So that's why I'm doing that. Okay? So we're good with that? All right, so that has everything going on with the mass. So I've got the force of the wind, the 2,400 newtons there at G. I've got the weight going down, and then I've got the 3 reactions at A. So I want to solve for those forces now. All right, so what if I want to do some 2D type stuff with this thing? How might I start if I want to start to solve? I think the thing to do on this, I'm going to start trying to find those cable forces. Can I get some information about those cable forces by doing anything kind of 2D style?
Got it down the y-axis.
Yeah, there's different ways to approach it. Down the y-axis, that came up, that'd probably be helpful. You could also start on the top and look down, like so, which I think is how I started. So if I'm up there looking down at the mast, what am I going to see that's really relevant to what I'm doing? I'm going to take a moment about A, I think is what I'll do, looking down, right down at it, okay? So there's A, and then the yard will kind of go to either side like that. So I'm looking right down the Z-axis. Now I could start with the Y-axis too, but I think I'll start with the Z in this case. All right, now I've got a bunch of stuff going on here, but a lot of it just cancels out. I've got the 3 reactions down at A, but they don't really make much difference because I'm going to take a moment about A. So that's RAX and what? I got RAY. Now my axes are a little goofy here the way I've got this drawn, but I've got X going this way and Y actually going down on this one. So RAY. And then I've got these forces going in towards A. They're not going to make any difference. Okay, and the ones I'm going to be concerned with are the ones doing this, aren't they? Okay. And that's going to be 0.546 FDC. And then 0.491 FEB. That's the only thing, if I take a moment about A, that's going to cause a twisting action, isn't it? Everything else is going right through that mast, pointing in towards it, okay? So what these things are doing is they're trying to kind of take the mast and do that with it. Those arrows are an attempt to draw in kind of an elevated XY plane up above, okay? That's what they're trying to do. There's nothing else that's counteracting those 2 cable forces. Okay? So I can write up a little moment equation, and in both cases the moment arms are 2.5 meters, and then I can equate EB to DC, okay? So what I'm dealing with essentially is just that, right there. Now, notice that even though what I'm working with here are certain components of DC and EB, that's the Y component, but all the same, what I'm doing is I'm solving for EB and DC. I'm not solving for just the Y component of EB and DC. I'm solving for the entire force. These are components of the entire force is what they are. Okay. So I know that FEB is 1.11 times whatever FDC is. Okay. So that gets me one equation with those two unknowns is what it did. I guess that, yeah, it pretty much is looking down the y-axis, isn't it? Yeah. All right. So I've got one equation with those two unknowns by taking moments about that mast at A, which I'm really taking moments about the z-axis is what I'm doing there. Y'all okay with that? Okay. All right, is there a second equation I can generate that'll get me another equation with those two unknowns? In the Z, I got RAZ though, that's gonna muddle that up if I try and do a sum of forces in the Z, because I got RAZ, which will be an extra unknown in there, so I don't think that'll get it for me. Well, I think any sort of sum of forces, we still got so many dang forces on that thing. I think we have to go with moments to kind of be sneakier, you know, kind of have a little more strategy and eliminate what we don't want, I think.
Take a moment looking down the x-axis.
Yeah, I think that'll do it, yeah. We'll pick up an unknown, that wind force, the 2400, well, it's not unknown, the 2400, but what'll counteract that'll be the two forces on the cable. So yeah, that's the way to do that, okay? So we'll take a moment about the x-axis this time. So what we're going to see when we do that is, I'm just trying to think where I could put this. So we got that mass coming down like so. And then we've got two forces pushing it out like that. We've got the 0.546 FDC and the 0.491 FBE. And then we got all this stuff going down here, you know, on the bottom of the mast. And then we've got 2400 doing that. And we got a few other random things going on here, but, you know, we don't care so much about them. We've got that weight going straight down, but who cares about that? That doesn't really make any difference. It's not going to cause any sort of moment here. And then we've got, you know, so we got that 900 going down. We've got some of these Z forces on the mast going down. We got all the reactions down there at the bottom, but really the only things that are causing moments, if we sum moments about the a-axis, or excuse me, the x-axis about point A, are these. So the 0.546 FBDC and the 0.491 FBE, that's kind of causing a clockwise moment. That's counteracting the 2400, which causes a counterclockwise moment. And then, of course, remember to include the moment arms on that. And then there's a good bit of algebra to go through on that one to get down to those forces. Okay. So I am taking a 2D approach here. It's just I'm starting off with that vector expression for the cable forces. That gets me broken up into components that I can use very readily to solve this thing out. So we've got both the 0.491 FEB and the 0.546 FDC times that dimension from the A up to the top of the mast, because that's where they are. And they're clockwise, so they're negative. And then I've got the 2400 times 3.9 meters, because it's applied down there. And that's counterclockwise, so it's positive. And then it's just a matter of collecting terms and doing a substitution. So I'm putting in that 1.11 FDC in for FEB, and that allows me to solve for DC, and then I can multiply that by 1.11 and I'll get FEB, which is 1869. Okay. So that gets the two cable forces, which are the hard ones. You know. Now what you got left is down on the bottom of the mast, you've got the three reactions down there, one in each of the three directions. So I would just use force equations to get those. Okay. Right? We good with that? All right, so that's just sum of fx, sum of fy, sum of fz to solve for rex, rey, and rez. So those are the reactions down at the bottom of the mast. So that's one way to approach that. So I started off by getting vector expressions for the cables, and I just kind of looked at it and said, well, how could I approach this and get those cable forces figured out? And I came up with a couple equations I could throw at that, moment equations. Okay. And then after I got the cable forces figured out, I could use force equations and solve for the reactions down there. Okay. So that's one approach. The other approach is on the next page, and that's doing a bunch of cross products. So similar to that problem with the car, we're showing both approaches you could use on these. The more kind of looking at it and figuring out a nice little strategy, 2D style, which, you know, probably is a little faster if you're, if you're comfortable with it. And you can kind of just get in there and just run the equations just that you need to solve for what you want. And then you've got the other approach that's kind of power through it, with the vectors, cross products. Either way. Now those cross products, they do seem to take a while, so that's the downside of that. And I just kind of worked it out for you there because it's just, it's kind of a lot to be copying down. Let's just say that. Okay. And again, what the cross products do is they just automatically generate the moments that you would do if you looked at it. Okay, that's what cross products do. They just kick stuff out for you. Okay. Good with that? So if we're going to do crosses here, you just take vectors from the origin in this case, which is point A, to the forces. So we got three forces. We got the two cable forces, and then we've got the 2,400 Newton force. So we just generate cross products for all three of them. All right. So that's pretty exciting there, as you can see. So what do we got there? We've got IJK, we got 2.5 in the X, 0 in the Y, and 5.1 in the Z, and then we've got FEB. So what we're doing there, we're taking the vector from EA to E and crossing it with FEB. FEB is unknown. I mean, we don't know the magnitude, but we know the three component component coefficients, you might say. And then do the same thing with FAD. So you take the position vector from A to D, and that's given by the dimensions on the mast and the yard. So you're going 2.5, and that's a negative in this case. And then you're going 3.9 and 1.2, so that's 5.1 in the Z. You're not going in the Y direction at all. So that's how you get from A to D. And then you cross that with the force vector. And then the last one is just the vector from A to the center of gravity, which is just 003.9, because it's 3.9 meters up the mast there. And then you cross it with the force vector, which is a negative Y vector. And then you just work out all three crosses, and then you collect terms in the I and J directions. And K, I guess I and K on that. Yeah, just I and K. Oh no, there's a J also. But anyway, you just collect the terms there and put them in a little bit of a matrix. And then you go ahead and solve. Did the Z equation first and got that FEB is 1.11 times FDC, and then did the X direction next. That's all just laid out for you down there, okay? So you can always run crosses. I mean, just take a moment about the point where most of the unknowns are, and that way you can solve for what doesn't act to that point. Okay, so we go ahead and set up all the cross products, run through and evaluate them, then collect them. So I've got rows for X, Y, and Z. The sum of them is 0. Solve out the Y, you could just as well, or the Z, either one, you'll get FEB as 1.11 FDC. And then solve out the X, and you'll get the relationship between FDC and FEB. And work those out. So FDC is 1681 and FEB is 1868. Okay. We okay with that? So the thing with that is just, it's a very reliable method, but it takes time. And as I've cautioned you before, nice and slow, and watch your calculations. Don't drop a negative at the top of the page, because that'll just blow everything up on you, and you gotta go find it. Okay, so so just very systematic in how you work through it. It's good habits to develop for when you work and all that. Okay, then you'd finish it up in the same way as the previous one, where you just sum forces in the X, Y, and Z directions. All right, so now you got a lot of stuff due Wednesday, so keep that in mind. I mean, so I hope you started that on the weekend. If you didn't, definitely start it now. I mean, that'll take you some time. We'll start going over that tomorrow. Okay. I'll get you one of these to do, but this one will be due Friday. I think you got enough going on right now. So, shall we? Yeah, I think it's 283. We'll make this due Friday. Oh, yeah, actually, right, there's Friday's off, isn't it now? Yeah. Well, that's interesting. Yeah, we'll make it due Monday. Just do it that way. So that'll be the 13th, I guess. Okay. All right. So I'll see y'all tomorrow.